Hey everybody, so last couple assignments I had previously, before we went on our little side tangent, had you guys vote on problems from the Foley, Factor, and Sketch assignments that you found the most challenging. So let's get into those two that you guys voted on. The first of those is problem number 6 from the part 1. Asks you to fully factor, then sketch this. I'm assuming, my hope is that the factoring part, or breaking it down, was the harder of the two. So let's get into that right away. So first step is we need to figure out all the possible x-intercepts of this polynomial. So in order to do that, there are going to be two things you're going to need to do. You're going to need to look at the last number, and then you're going to need to look at the first coefficient. The last number, I need you to write down the factors of that number. So again, factors of 6 are 1, 2, 3, and 6. Secondly, I need you to take 6 in the front and write down the factors of 6. Again, the one on the front, I need you to write that on the bottom of this. So 1, 2, 3, and 6. What you're going to do is pretty much take each of these top ones and divide them by each of the bottom ones. So all the different combinations there. So 1 divided by 1, 2 divided by 1, 3 divided by 1, 6 divided by 1, 1 divided by 2, 2 divided by 2, 3 divided by 2, 6 divided by 2. And you keep going through until you've taken every single one of these top ones divided by all these ones on the bottom. And then you're going to create a list of possible x-intercepts in that fashion. So 1 divided by 1, 2 divided by 1, 3 divided by 1, and 6 divided by 1. That's our first batch of x-intercepts. And remember, with these, you got to think of them not only as positive versions, but also negative versions of themselves, because it could be either positive 1 or negative 1, positive 2, negative 2, so on and so forth. Now let's take each of these top numbers and divide them by 2. So 1 over 2, 2 over 2. 2 over 2 is actually 1, so we don't have to list that again. We got 3 over 2, and then 6 over 2, which is 3, so we're not going to list that again. Let's go on to the next round. 1 divided by 3. 2 divided by 3. We don't have any of those. 3 divided by 3, which is 1, and then 6 divided by 3, which is 2. So we already have those. We're good to go. And then the last round, let's divide each of these by 6. So we're going to do 1 over 6. 2 divided by 6, which actually reduces to 1/3. We already have that. 3 divided by 6, which reduces to 1/2. We already have that. And then 6 divided by 6, which reduces to 1. So we already have that. So this is our options in terms of x-intercepts of this, or potential x-intercepts of this polynomial. At this point, you would just start by dividing this by whichever ones you'd like. Now I usually start with the whole numbers and then work my way, if they don't work, any of the whole numbers, and work my way down to the fractions. And that's what I would do next. And you're going to take these and divide these into that. Now the easiest way to do these, because these are roots, is to use synthetic division. So let's start by, I usually start with 1. Let's test the x-intercept of 1 for this polynomial. And again, we're looking for remainders of 0 when I do this division problem. If you get a remainder of 0, you're good to go. So we'll drop this down. Got 6. 1 times 6 is 6. Plus that is 11. Got 11. Negative 17 plus 11 is negative 6. We got negative 6. And that, unfortunately, gives us a negative 12. That is not a remainder of 0. So 1 is not an x-intercept. Let's try, for instance, negative 2. So negative 2, same polynomials, 6, 5, negative 17, and negative 6. Drop that down, multiply it, we get negative 12. Multiply that, you get negative 7. Times that, you get 14. Get negative 3. Negative 2 times negative 3, you get 6. And what do you know? I got it to work, y'all. So I got a remainder of 0. Once you get to this step, once you found that this is truly an x-intercept of that polynomial, we can break down the polynomial. So we do that by, first of all, writing this in polynomial form. So putting in x squared, an x, and then leaving that a number. And remember, this is just the remainder, so you don't have to write that part. So this would be 6x squared minus 7x minus 3. And then we're going to multiply that times the factor version of this x-intercept. So this x-intercept is negative 2, but what factored version like what is the factor that gives you that x-intercept? Now, some people might say, well, isn't it just x minus 2? Well, if you set this equal to 0 and solve, you would actually end up getting x equals positive 2, which is not what we want. We want x equals negative 2. So we need to set up a factor that will get you back to this x-intercept. So the factor of x plus 2 would do the trick of that. So we're going to write that factor out front. So x plus 2 times this polynomial actually gets us back to this polynomial. So the polynomial division just helps you figure out what, in this case, x-intercept goes into it, and then you multiply that factored version times what you're left with, and then that is a way of breaking down that polynomial. So at this point, this should be factorable, which hopefully it is. At this point, you would break out your, the Japanese method or whichever way you do factoring, and you would just go ahead and factor it. So let's try the Japanese method for those of you guys who like to do that. So I need two things that multiply to get 6x squared. So that could be what, 3x and 2x. And then two things that multiply to get negative 3. So that the only options here is 1 and 3. So I'm going to go, let's see here, 1 and then negative 3. To check your work again, you would crisscross. So 3x times negative 3 would be negative 9x. And then 2x times 1, which would be positive 2x. And you want to make sure that these two things add up to the middle, which they do. So the way we write this, again, is 3x plus 1. And then 2x minus 3 across the bottom. So this would be the factored version of that original polynomial. At this point, to sketch this graph, you would get the x-intercepts of each of these. So set these all equal to 0 and get those 3 x-intercepts. So I'm going to kind of speed this process up. So we have negative 2. This would give you negative 1/3, which would be somewhere around there. And then this would give you positive 3 over 2, which is 1.5, which would be somewhere between 1 and 2. So those would be your 3 dots. Now a quick recap again of how to sketch these. You can go back a few videos to take a look at that, but what you need to know is the degree of this as well as the leading coefficient. So the degree is 3, that's an odd function. The leading coefficient, that's a positive, so that would mean that left arrow is down and the right arrow is up. And then sketching this graph, none of these are like double roots, so none of these bounce. So you're just going to be going through each of these dots like that to connect the two arrows. So that would be how you would sketch it. Let's go on to the next problem that you guys said you had issues with. This one's going to go a little bit faster. So taking these two numbers, so factors of 3 is just 1 and 3. Factors of 12, well, there's few. 1, 2, 3, 4, 6, and 12. So getting a list of these, you would have 1, 3, and then we're dividing both of those by 2, so 1/2 and 3/2. And then we do 1 divided by 3, and then 3 divided by 3, which we already have, is 1, so we don't have to do that one. 1/4 and then 3/4, so we don't have those. And then we'll do 1/6 and 3/6. 3/6 is 1/2, so we will skip that one. And then lastly, 1/12 and then 3/12. 3/12, by the way, is just 1/3, or actually, sorry, 1/4. We already have that, so we don't have to list that. So again, think all these plus minus, plus minus, plus minus, all the way through. So these would be all the potential x-intercepts of that polynomial. So let's start by dividing. So we're going to take this, write it 12, 16, negative 5, negative 3. Let's try, for instance, 1. That's usually what I start with. Drop down this, you get 12. 12 times 1 is 12. 16 plus 12 is going to be, what is that, 28. 1 times 28 is 28. Negative 5 and 28 is 23. And then 1 times 23 is going to be 23. That's going to be 20. Remainder of 20, that doesn't work. Now, what I've noticed is, I'm just going to skip ahead a little bit. I tried actually 1 and 3. None of them worked. So it must be one of the fractions. So let's do fractions. Let's try, for instance, 1/2. So 1/2, 12, 16, negative 5, negative 3. Drop that down, get 12. 1/2 times 12 is 6. 16 plus 6 is, what is that, 22? Half of 22 is 11. Negative 5 plus 11 is going to be 6. Half of 6, 1/2 times 6 is going to be 3. And voila, there we go. We got our, we got one of the factors that give me that. So I'm going to write this in polynomial terms. So this is x squared, x, and then the number. So 12x squared plus 22x plus 6. And then I need to write this not as a fraction, but as a factor. Now, some of you guys might say, like, well, could I do something like this? And the answer is, yes, you could. Be weird, but you could totally do that. Now, when you're dealing with fractions, writing factors, typically what will happen is this number is the thing that's being plus or minus 2x. This is the number that would be attached. So actually the better way of writing this would be 2x minus 1 as a factor. Because again, set this equal to 0, you'll see that this gives you 1/2, right? You would add 1 and then divide by 2. So again, 1/2. So this actually would be the better way of writing it. So let's go ahead and write that like that. 2x minus 1. So this is the answer, times 2x minus 1 gives you back to your OG polynomial. Now this should be technically at this point factorable. Now to make my job a little easier, I'm going to factor out a number. So I'm going to write 2x minus 1. I'm going to factor out times, each of these is divisible by 2, so I'm going to factor out at 2. That would turn this into a 6x squared, a 11x, and then divide that by 2, and you would get a 3. Now I would just go ahead and factor that. So 2x minus 1. Technically, this 2 could actually go all the way out front if you'd like. And then we're going to break down that factor. So again, Japanese method, whatever you'd like. I'm just going to go ahead and show you the answer to this. So it'd be 3x, 2x. And then this is going to be plus 3. This is going to be plus 1. And then that would get you the factors of 6x squared plus 11x plus 3. So this would be the factored version. At this point, you would set these equal to 0, and then that could help you then get the X intercepts, and that would get you your, at least what you would need to do the sketch. Okay, so hopefully that helps with those two problems for those of you guys who are struggling. All right, on to the last part of the unit. Actually, more of what we already know. We're going to put everything together. So the reason why we went on that quick little tangent into roots and imaginary numbers is sometimes the roots or intercepts, you might say, of these polynomials will not be always real. Let me give you a for instance of that. So we're going to, in this problem, fully factor and then look for all the roots of this polynomial. Now, to make this problem just a little bit easier, I'm going to rethink of this because it's missing its x squared term. I'm going to think of this as x cubed plus 0x squared minus 5x plus 12 for making this problem just a little bit easier for me. So I'm going to start by getting the possible x-intercepts like before. So I'm going to look at this number and then the number out front. In this case would be a 1. So there are going to be no fractions here. It's going to be just all strictly numbers. What are the factors of 12? So we already did that. So 1, 2, 3, 4, 6, and 12 over the factors of 1 is just 1. So you don't have to divide any of these other than just 1. So this would pretty much be our list. Plus or minus 1, plus or minus 2, plus or minus 3, plus or minus 4, plus or minus 6, and plus or minus 12. Okay. At this point, we would go ahead and see if we could figure out what would be, which one of these would break that down. So I'm going to try, let's say, for instance, 1. So let's go 1, and we'll put that into that. We're going to write this in polynomial or synthetic form. So 1, 0 as a placeholder, negative 5, and then 12. And then let's start over. So drop this down. 1 times 1 is 1. 0 plus 1 is 1. 1 times 1 is 1 yet again. Negative 5 plus 1 is going to be, what is that? Negative 4. Negative 4 times 1, well, that's not going to get me a remainder of 0, so that doesn't work. Let's try again. So let's try maybe 2. Again, we're just going until we find one that actually does work. So drop this down 1. 2 times 1 is 2. 2 times 2 is 4. Negative 5 times that is negative 1. It's negative 2. That's not going to work either. Crap. All right, so let's try, let's see here. Let's try negative 1. I haven't tried that one yet. 1, 0, and negative 5, 12. Drop that down, we get a 1. Get a negative 1 this time. 0 and that, make negative 1. Negative 1 times negative 1 is, what is that? 1 is going to be negative 4. Crap, that doesn't work either. So let's try, let's do negative 2. So sometimes, you guys, this will take a minute, and the reason why I'm showing you this, I'm doing all the work. I actually don't know which one of these will work, so this is why this is taking a while. I want you to understand that there's really no rhyme or reason to sometimes how this works. So this would be negative 1, this would be 2, so again, that doesn't work either, because that's 14. So none of these have worked so far. Let's try 3. So again, the reason, I'm doing this is sometimes this does, and I've done these for a while, you guys, this does take a while. So this part is why synthetic division makes this at least bearable. If you did this with long division, this could take all morning, to be honest. Oh, I think we got a breakthrough, y'all. So negative 5 plus 9 is 4. 3 times 4 is 12. Ah, crap. I'm so close. So let us maybe try negative 3. Because that would, again, be 24, and that's not it. So let's try this one. Hopefully this will be the jackpot. Drop this down to get 1. Negative 3 times 1 is negative 3. 0 minus 3 is negative 3. Negative 3 times negative 3 is 6. No, sorry, 9. Negative 5 plus 9 is going to be 4. Negative 3 times 4 is going to be negative 12. And there we finally go. Heck yeah. All right, so this guy is going to be the polynomial version. That's the x-intercept that would work. So we're going to write that as, this would be x squared. That would have an x, and then that would be plus 4. And then this just needs to be written as a factored form. The factored form of the x-intercept of negative 3 would be x plus 3. Because when you set that equal to 0 and solve, that would get you an x-intercept of negative 3. Now, normally at this point, you would go ahead and factor this. And I urge you to go ahead and try, but the problem is you are not going to get it to factor. So at this point, you would be done. If they were asking you to fully factor it, you would stop at this point. This would be the factored version of that original polynomial. Again, this will not factor anymore. So if they ask you, well, what are the roots of this? There's really only one real root. There's this one. When you set that equal to 0, you get negative 3. So x equals negative 3. That's one of the roots. However, you can't factor this, so how do I get the x-intercepts of this? Well, enter, again, the quadratic formula. I know we haven't been acquainted for a while, but the quadratic formula is when something doesn't factor. This is the only other way to get x-intercepts. So let us do the quadratic formula for this and see what happens. So quadratic formula again is x equals negative b plus or minus the square root of b squared minus 4ac all over 2a. So let's plug in what we know. So a would be 1, b would be negative 3, c would be 4. So plugging that in, I would get negative 3, which would end up being just positive 3, plus or minus the square root of negative 3 squared minus 4 times 1 times 4, because that's c, all over 2 times 1, or 2a. Cleaning this up, this would be 3, negative, plus or minus the square root of 9, and this is 4 times 1 times 4, which is 16, minus 16 over 2. And then going even further, you'd have 3 plus or minus This would be negative 7. Square root of negative 7 over 2. Now, normally, this is where you would say, all right, square root of negative, you can't do that. There is no other roots. It's true, there are no other real roots. However, there are imaginary roots for this polynomial. So if you were to simplify this, learning what we learned last time with roots and complex roots, you could break this down to negative 1 times 7. So you could really write this like this: 3 plus or minus root of 7 times I over 2. So technically, there would be 2 more roots of 3 plus square root of 7i over 2 and 3 minus square root of 7i over 2. Plus that root we found before of x equals negative 3. So these would be all 3 of the roots. Putting this full circle, the degree actually tells you how many roots an equation has. Doesn't necessarily always guarantee you there will be real roots, but there will always be that many roots. So a degree of, for instance, 5 would actually mean that there would be 5 roots to that polynomial. Because this degree is 3, we always will find 3 roots. Again, not always all of them will be real roots. All right, last but not least, we got one. All right, on to the last problem. So we're going to go ahead and try this one out, and then you should be able to get started on that assignment. So we're going to fully factor this and then look for all the roots of it as well. So let's start with writing all of its possible x-intercepts. Again, taking this and this. There's really only, think of that as 1, so there's only one factor of 1 is 1. And then writing down 12 again, we got 1, 2, 3, 4, 6, and 12. Dividing all those by 1, those are going to give us our possible x-intercepts: plus minus 1, plus minus 2, so on and so forth. This is very similar to the last problem we just did. So let me put those down. So those are the possible x-intercepts. We're going to now divide those by these until we get that to actual breakdown. So let's start with, let's try negative 3 first. It's lucky for us last time. Let's see if it is again. So we got 1, 2, 1, 8, negative 12. Drop this down, we get 1. Add those together, you get negative 1. Multiply that together, you get 3. Add it, you get 4. Negative 3 times 4 is negative 12. 8 minus 12 is going to give us negative 4. Multiply those, and what do you know? First try, got that out, and that works, okay? So I'm going to write this now as a polynomial. So this would be negative 4. This would have been x squared, x cubed. So it would be x cubed minus x squared plus 4x minus 4. And then the factored version of this would be x plus 3. Now, like last time, if you're dealing with x to the 4th polynomials, you'll break it down, get one of the x-intercepts or factors, and then you're going to have to restart the problem over again because this one, unfortunately, cannot be factored. So what we're going to do is we're going to think of this as a new problem and write down its possible x-intercepts so that we can, again, have a smaller number to deal with of potential x-intercepts. So in this case, we're really only thinking of plus minus 1, plus minus 2, and plus minus 4 because those are the only factors of 4. Let us try out 1. We're going to divide this now by the x-intercept 1 to see if that will work. So the coefficients of that smaller broken down polynomial. So we're going to get 1. 1 times 1 is 1. 0. 1 times 0 is 0. 4 plus 0 is 4. 1 times 4 is 4. And first try again. It's like I already knew the answer or something. All right. Anyway, so that's going to be a intercept as well as positive 1. Okay. So we're going to write this down. This would be x squared plus 0x. What's that? Plus 4. This in factored form would be x minus 1. Set that equal to 0, you get a x-intercept of 1. And then from previous, we already found this was a polynomial as well, or a factor as well of this polynomial. So we're going to put that out front as well. And this is what we had talked about last time on how to do degrees 4. So you kind of break it down twice, kind of remembering all the factors you've gotten along the way. So x plus 3 times x minus 1 times this. At this point, we should be able to either A, solve this by quadratic formula, or B, solve it by factoring. Problem is, you cannot factor this, which again, we're having issues. But if I set this equal to 0, like I could set these equal to 0 to get the roots, technically I could solve this. So at this point, this would be the fully factored form of that original polynomial. But if I wanted to get the roots, I would set each of these equal to 0 and solve. So x plus 3 equals 0. You would get back your negative 3, which is one of the roots. X minus 1 equals 0. Add 1 to both sides. You would get 1. There's another one of the roots. And then this, x squared, technically you don't have to put plus 0x. You could just put the plus 4 equals 0. You could solve for that as well. So subtract 4 from both sides, square root it. You would end up getting x equals, remember, plus or minus the square root of negative 4. Now, normally this would be where you'd stop and be like, well, these aren't real. You can't square root a negative number. But we do know that we can simplify this negative root. And that would just be simply writing x plus or minus. Negative 1 times 4, square root of negative 1 is I. And the square root of 4 is 2, so that would just be 2I, plus or minus 2I. So this technically would have 4 roots, negative 3, 1, and then 2I and negative 2I. Again, because the degree is 4, we are guaranteed 4 roots. Not all of them have to be real. So putting everything together, this would be everything for polynomials that could come up while factoring or potentially just looking for roots of those polynomials. So today, you'll have a little bit more practice with imaginary or complex numbers, along with some more problems like this to tie it all together. If you have any questions, again, office hours are daily, Monday through Thursday, 1 to 2 p.m. If there are no other questions, you guys have a wonderful day.